This is Lab 18, and we're going to talk about hierarchical, if I can spell that, clustering, and this is associated, of course, with lecture 18 on the same topic. And so we're going to look again at our favorite data set, our iris data set, and we're gonna just remove the species column. So we can say which of my columns, it's called species, put a negative sign, that should remove it. If things work nicely, that's not how you spell species, so that would cause an issue. Okay, so let's see if this works. There we go. So we actually will call that data, and I look at my data, right? It has my photo variable, sepal length, width, petal length, width. And the reason I like this data is because it has a true underlying known group structure, which is the species, but in reality, you wouldn't really know that. So I can do some hierarchical clustering with the function hclust. So again, this is built into the base of R. It's just a real basic classic method. So we do hierarchical clustering. So hclust takes a argument D, and you wonder what D is? D is our dissimilarity matrix. And it takes a method. Here is complete for complete linkage. The agglomeration method to be used. And there are some other ones we didn't talk about. These word ones, but a single, complete, and average. There's some other ones you could use here. But these are dissimilarity structure or matrix produced by this function dist. So in order to apply this method, there's a whole bunch of other crap here. In order to apply this method, of course, we need to use the dist method, which is our distance matrix computation, or dissimilarity more generally. So this will calculate a distance matrix for numeric data, and maybe we will look at an example of how to do this. There are other functions for calculating dissimilarity matrices for categorical stuff. It's a little more advanced for ordinal stuff, or you can come up with your own. But all you need ultimately is just this dissimilarity matrix. But if I have my numeric data, I can create my dissimilarity matrix D by calling dist on my data, and it needs to be a matrix, so I'm going to call it as.matrix, because originally it's a data frame, and that will cause issues. And if I look, here's my dissimilarity matrix, right? So we have 150, it should be about 150 by 150. Now, I believe this is not actually a matrix, it has some other weird class. This class of dist. You can make it a matrix using as a matrix, but it's 150 by 150. Let's just let's make the matrix version dmat. Okay, so for example, I can bring up the first 5. The 0 is down the main diagonal, and it's symmetric, right? So is that symmetric? D should say yes. Is that symmetric not a function? I can always take D and I can subtract off its transpose. This better give me a bunch of zeros. So so this should tell me this is true. Yes, this is true. Everything is, so this is a symmetric matrix, right? So that's my dissimilarity matrix, this is in a matrix form. You actually need the dist object, so you actually need this D when we pass it to hclust. But using my hierarchical clustering method, hclust is pretty easy. So I can say hclust, and I pass in my dissimilarity matrix, and I can say my method, maybe I want to use average clustering. And I run it, and it gives me an error because I can't spell average. If I respell average, I run it, and it doesn't give me an error. There's some nice functions associated with hclust. I can plot it, and it plots my dendrogram. Now here's a kind of more complicated dendrogram than we saw in the kind of toy examples we looked at in the lecture, but here's my dendrogram, and it groups everything, it agglomerates it. So at the bottom, they're all individual, and it groups them, it kind of recursively adds things together and builds up my structure. We can try different methods of clustering. If I can talk, we can try them. So I could try a complete. We had a different looking structure. So the clustering structure, the clustering method, the measurement, the group distance between my clusters does matter, and I can do single linkage and see what that looks like. So you see, you can get things that look slightly different or very different. So you have to be a little careful and try and over-interpret a dendrogram. It's not anything particularly inherent in the data insofar as, I mean, it depends on the clustering method we use, and you'll get different dendrograms. So this gives me a very different dendrogram, and therefore it can give me different clusters and different hierarchy of clusters than if I use, say, an average or a complete. I'll get a different answer if I get a single. So beyond just looking at the dendrogram, we can also actually get cluster assignments. And we get this with the cut tree method. And it says cut a tree into groups of data. And so basically I pass it in my tree or my clustering tree, and I pass it either k, which is the number of groups, or h, which is the height which should be cut, right? And that's what we're talking about in lecture. If I'm going to cut this at various points, you have the chunks kind of fall off as clusters, and you'll get the actual clustering. So it's basically h would be the kind of, if you did this hierarchical clustering but stopped at a certain point when my distances between my clusters got beyond h, this is the clustering we would get. Okay. So we can use this to get some clusters. Let's say, and let's cut it at, well, let's look at our dendrogram. What's a reasonable value? Cut it at, I don't know, 0.25? 0.5? Let's say 0.5. So h is 0.5. And this gives me apparently 10 clusters. Look at different sizes of these. Most of them are in cluster 1, 3, and then there's some other smaller ones. And so one way to visualize this is I can just add a line to my dendrogram at h is 3, and I say maybe to make it a red line, right? So basically what I've done, oops, not 3, why did I say 3? It's 0.5, right? Is I basically cut there, and so you can see if I cut there, I'm going to get apparently 10 groups. Now, you could cut in different places. If I cut at 1, I should get 2 groups, this cluster and this cluster, right? So if I cut at 1, I should get everything in one cluster. Oops. Well, that's a bit strange. One would think I would get 2 clusters. Let's just move this down a little bit. Oh, you know why? Because I'm cutting it. So, yeah, let's be careful. I have to specify I'm cutting at a height of 1. There we go. Now I get 2 clusters. Okay, as we think. You can also, as you just saw there, I can cut, but I can specify k as the number of clusters. So if I say I want 3 clusters, that will give me 3 clusters. So there are kind of a couple different ways of doing that. Maybe the last thing we'll do here is we'll do something similar to what we did last time, where I could plot, if I did an SVD of my matrix here, and maybe I want to scale this thing. And I do the SVD, I basically do PCA, so I'm going to grab up the U components of my SVD, and maybe I'll grab the first two. And I'm going to get some clustering, so maybe my clusts, I'm going to say, there's 3 groups I grab from there. We know there's truly 3 groups in our data, in some sense. And I can color it by those clusts I get. So if I do this, this is the clustering we get. So not amazing. I mean, it's not really the true groups in my data, quote, true groups in my data. You see one big black with Setosa and then this other one, but we have these 2 green ones, which are this other cluster. That's not super great. But you could play, this was using single linkage. Maybe I'll try average linkage, and then I'll cut to get 3 groups, and then I'll plot that. We try this. That looks a hell of a lot nicer. So when I use this average linkage, I'm getting pretty much my 3 true groups back there. So that's pretty cute. And I could even add text to my data. What do we call it? Is it label? There we go. And so you see that my Virginica are basically the green, the red of the Versicolor, and the Setosa are the black ones there. And it doesn't do a perfect job of clustering, but it does a pretty good job at recovering that true underlying group structure. That's actually quite impressive. We can kind of visualize it, PC1 against PC2. I mean, you can also, for example, you can look at higher order PCs. There's nothing stopping you. We're looking at 1 against 2. We could look at 2 against 3. That would give me a slightly different slice of the dimension. It's a little messier, but it's worth looking at generally. Okay, so I think that's a pretty nice quick overview of hierarchical clustering. Last time we looked at k-means, so today we've gone over hierarchical clustering. Those are kind of 2 big clustering methods out there, kind of real classic ways of clustering your data.